Hello, this is going to be test prep for tutorial test number 6 in 2018, and this is because of the lack of the midterms this year. We are out of sync with the previous test, so we're looking at tutorial test number 5 from 2017 in ENGPHYS 2P04 Applied Mechanics. Okay, so what we are dealing with here is we got this rigid member A, B, C, D, E, and DG is also rigid there, and we have these two external forces applied, and we're going to look at how this thing moves around. So this member BF and member and this other one here CH, these are not rigid. Instead, they give us a Young's modulus for these. Now, because they are pin supported, we are only going to be dealing with the normal force in this. So the change in length that's produced for this, not dealing with any kind of a buckling effect for now. Okay, so what we'll do is we will grab this and then paste it over into paint.net. I've already done that, and we can go and analyze the net force on the different components. So first I'm going to look at this thing by itself. Yeah, there we go. Okay, so I'll paste that over there, and then we can draw on some force vectors on this. So we're going to have a force there, and that is 1 kilonewton over to the left, and we're also going to have a moment that's applied on this, and the moment, let's see here, is going to be pointing in the other direction. And how much is this going to be? Well, now we'll look back at the distance away, and that's 0.2 meters and 1 kilonewton that way. So that's 200 Newton meters. Okay, so now that we've got that, we can we'll know how much force and moment is translated over to A, B, C, D, E, which is what we're really interested in here. Okay, so we'll go and grab that and paste that down over here. And then from this one, we know that we're going to have a 1 kilonewton going to the left at the top and a 200 Newton meter in the, not counterclockwise, but clockwise direction applied to this. And then you can just check that things have worked out correctly. So looking at this force up at the top here, that would tend to rotate this thing to the right and cause a force to the right as well. Okay, so that kind of makes sense for this. So let's just draw those things translated over here. We've got the moment applied, 200 Newton meters. The only reason I'm using different colors here is to make it easier to tell which is which label applies to which, and 1 kilonewton there going to the right. Okay, so that's all good. Now, while we're here, we can also label the other forces. So we're labeling these in tension by default. And for AX and AY, we can draw those in whatever direction we like. So let's call that AY, AX, and this one is BF, and this one is CH. Okay, so we draw those in tension by default so that we can keep the sign convention, and that way we'll know at the end if we have a positive BF, that means it's tension, and a positive CH will mean that it's tension. Now, looking at this, in this case, we can tell that because all of the forces are tending to rotate this in a clockwise direction, BF will actually be in tension, so it'll be extended, and we expect a positive answer for that one, but CH should be in compression, so we expect a negative answer for this force. So CH will be negative, which means it's actually pushing up. So if we have a negative force in the downward direction, those two cancel out, and we'll have a force up in the other direction. Okay, so we can grab that and then paste it back over here if we like. And now we're ready to use to write out some equations for this. So we got our computer algebra system here. We've got some force equations, and that's going to be the first set. So we're going to have force equations for the net force in X, which would be AX plus 1 E3, 1 kilonewton to the right, and that's going to be equal to 0. The equal 0 is implied in Maple. Then we've got A in the y direction, AY plus BF minus CH and minus 2 E3. And then the moment, the net torque about, let's say, point A in the, let's say, counterclockwise is positive, so out of the page direction. That would be BF times its distance away, looking at this top diagram here that has the distance labels still in it, BF times 0.15. You don't need to write the 0, that's implied. So 0.15 meters minus CH times 0.15 plus 0.25 is 0.4. And then we've got a minus 200. That's just going in the clockwise direction, that pure moment. And then minus 2 E3 times the total distance, which would be 0.4 plus 0.15 is 0.55. Another 0.12 is 0.67. Okay. Now, the 1 kilonewton to the right doesn't create any moment because we are ignoring the thickness of this beam. If it did have a thickness, so if it was actually like 2 centimeters thick, say, then we'd have to multiply this by the 1 centimeter displacement that it is from the center line to figure out the torque that this creates about point A. So that's the force equations. Now we can't actually solve these because we have too many unknowns. So you see we have CH equals CH. That's the thing that Maple will return back if you have too many unknowns for the number of equations that you have. And that makes sense. This is over constrained. We've got 1, 2, 3, 4 unknowns, and we only got 3 equations for net force in X, force in Y, and torque about point A in 2 dimensions. So the next things that we're going to need to, so before we can solve this, we're going to need additional equations, and we can get those by writing out spring equations and then geometry equations. Let's explain what we're talking about here. So these members BF and CH are elastic. They have a Young's modulus given in the question here of 1 gigapascal. And they've got some areas associated with them. So let's see. BF has an area of 3 square centimeters and CH has an area of 6 square centimeters. So we can put those in. Let's look at those parts of the screen. So BF is equal to 3, and square centimeters in SI units, so in units of meters squared, would be E minus 4. So a square centa is a E minus 2 squared, so that's 10 to the negative 4. And the area of CH is 6 E minus 4. Okay, so the spring equations are telling you about how much are using Hooke's law. This is like stress equals Young's modulus times strain. So the stress is the force, BF, divided by the area, and that's equal to the strain, which is the strain times the Young's modulus. So Young's modulus times strain, which is the change in length, and we're going to write out what that is, divided by the original length, which is 0.2 for the length of BF there. Yeah. Now the other one that we're going to have for CH would be CH divided by its area is equal to its Young's modulus times its change in length over its original length, which is 0.25. And that's the principle for the spring equations. Now, the way to get the to have this make sense and make it merge with the geometry equations later is to write out these length increases. So because we're writing a tension stress here, we have to have the tension stress, so the amount of force that per unit area that it has from being extended is related to the Young's modulus times the fractional amount of extension that it has. So this has to be the extension length change, so the increase in length per unit length. Increase in length based on the geometry here, and really make sure that this makes sense to you, is negative the displacement of point B. So we're just going to call that YB for the displacement of point B. So if the y coordinate of B has moved up, then BF has actually decreased in length. But if YB has moved down, then BF has increased in length. So the amount that it's increased in length is negative the y displacement of point B. And then same thing for point CH. Because point H is fixed, we can say that this is actually positive YC. So the reason this one's positive and this one's negative is because BF is on top of the member. So if this moves down, this has to move down for BF to increase in length. But CH is below the member ABCDE. So YC has to get larger for this thing to increase in length. Okay, that's the spring equations. Next, we have the geometry equations. So the geometry equations represent relationships between the y coordinates of all the points. And because this is all in a line, we can say that YB divided by 0.15 is equal to YC divided by 0.4. So this is representing the fact that A is fixed. And so the amount that B moves up is divided by its length is from similar triangles equal to the amount that C moves up divided by its length. Yeah? And then same thing, the question actually asks us about the displacement of point E. Yeah. So the amount that point E moves up divided by the total length is also related to either of these. So we can pick whichever one we like. Let's say YB. Okay. So now we've got spring equations, geometry equations, and the force equations. And these all together are enough to solve. So first, I'm going to make a list. After opening up each of these sublists. And so you see this, this OP command just opens up the previous list. So without that, we would have a list of lists. You see, so list of lists, which is not going to be what we want to solve there. So that's why you have to use the open command there. Okay, and now we can solve this thing. Yes. So what have we figured out? We found out that AX is negative 1,000. Okay, we got to pull to the left. That makes sense. YB is negative about 0.5 millimeter, so it's moved down about that. We expect YC to move more than twice that because it's more than twice as far away. And yes, so it's moved about maybe close to triple that. Makes sense. And YE has moved about double YC, not quite double, but almost double because it's about twice as far away. So this all kind of makes sense. And let's see, AY is negative. We're actually pushing down there, and BF is probably taking up a fair bit of force up. It is, but actually CH seems to be doing the bulk of the heavy lifting, so to speak here. It's holding the thing up. Okay, so there we go. So the next thing would be the shear force and bending moment diagram for this. And for that, we're going to need a new diagram. So let's go with, I want to make a slice in this somewhere to show the direction of the force. So maybe I find it most convenient to just kind of cut off the very end of the thing. So let's get a lasso here, and we will slice through this like that while keeping the labels in. Okay, so we've got that thing, and we can paste that somewhere else. Oh, you know what else we could do? Since we've already copied this thing, let's just make a rectangle, which is gonna block this out. Great. Okay, so now that we've got that, we can zoom in and draw the internal shear force direction, normal force direction, all that. I don't think the question actually asked us to put the normal force in this, but we can. So that'll be our normal force. We'll just label that N. We've got a shear force, which we'll use the standard sign convention and draw that down. And we've got a bending moment. I don't know, maybe gold here. And the bending moment is by default in this up direction. Yeah. And this is a useful construction for coming up with the formula that we have for the internal shear force and bending moment diagram. Okay, so let's see. We don't really need to show the output of that. We are going to need the output of the solve command, and then we'll assign it. Then we need to define the things inside there. So N, let's see, N is going to be equal to negative AX minus piecewise if X is greater than the distance to point D, which is 0.55, then 1E3. V would be equal to AY plus if X is greater than 0.15, then BF plus if X is greater than 0.4, negative CH, plus if, actually, I guess there's nothing applied at point D, so that's it for the shear force. And the bending moment, we can say that the moment is equal to the integral of V from X equals 0 to X, and then add in the piecewise moment. X is greater than 0.55, that's applied at point D. And check that that is going to be increasing the amount of bending moment we have applied at the end. Let's check if this looks good. Okay. So we've got a normal force, which is just 1,000 until we pass point D, and then there's no more normal force, and that's because there's nothing else happening at the end here in the X direction. The shear force starts out at negative 2,000, counteracting AY, and then jumps up after we pass BF, jumps up a lot more after we pass CH, and at the end is just sort of doing the same work as the 2K would be applying at the end there. The moment starts at 0 and ends at 0, which is what you'd expect if you don't have any point moments applied at the start or the end. So everything looks good. Okay, the next part of this test is dealing with stiffness and compliance matrices, and these tell you about how the object is going to be deforming. So we can jump over to the lecture notes here, and in the lecture notes we define stiffness and compliance matrices in this part under the heading test 6. I'm not sure if you guys have those headings, but anyway, it might be under a different top. You should have these headings. Yeah, we'll make sure that you let me know if you don't have them, and we'll fix that. Anyway, under the stiffness and compliance matrix section, we are just sort of writing out in equation form how the strains in the different directions are related to the stresses in those directions. So we've got the strain in X, Y, and Z as a vector given by 1 over E times this matrix times the stress in those directions too. And then we've got examples of how you would type that out using linear algebra and matrix things. So you can literally just take this and copy it and paste it into Maple, but just check that the code actually works. But I encourage you to think through it and then decide what to type in Maple yourself there. Okay. So back up here, looking at the equation, we need to get that we're going to write out an equation that is relating the this matrix here, that is using this matrix here to relate the stress to the strain. Now, by the way, this thing, which is relating the stress to the strain, is called the compliance matrix. So the compliance matrix, if the thing has more compliance, then the stress will lead to, a certain stress will lead to more strain, and that kind of makes sense. So the stress times the amount of compliance it has will give you the strain. Inversely, the strain times the amount of stiffness it has will tell you how much stress needed to be applied. So the stress is equal to the stiffness times the strain. And I guess because engineers have a strange sense of humor or something like that, the symbol for the compliance matrix is an S, while the symbol for the stiffness matrix is a C. So they're kind of reversed like that due to some running joke that has gone on probably too long. But anyway, now you're part of it. So the compliance matrix is the one with the S, and the stiffness matrix is the one with the C. Maybe this was something to do with why certain things like propane tanks are threaded backwards to make sure that you're thinking when you're using them. Because if you just go and do what's natural, you'll actually open it when you're trying to close it and all that. Anyway, let's just jump back into typing this out. Okay, so we've got the linear algebra package installed to be able to use matrices, and then we'll say that S is equal to 1 over E times matrix 1, negative nu, negative nu, negative nu 1, negative nu, and negative nu, negative nu 1. Close out that, and that should work. Yeah, okay, there we go. So there is our compliance matrix, and we can figure out the stiffness matrix by taking the matrix inverse of S. There we go. All right, and looking back to the actual test that we've got here, because we know the Young's modulus is 4 and the Poisson's ratio is 0.3, we can put those in. And that will evaluate to the numeric versions of the stiffness and compliance matrix. Now here I've just typed in 4 instead of 4E9, and you can do it that way. You can include the full decimal fractions of it, or you can just leave it as 4, and then remember that you're going to have gigapascals for all of the answers. So this sort of switches the units that things are in. Up to you which version you wanna go with. Okay, so next thing we're gonna do, so that's the first part, figure out the stiffness and compliance matrix. Wow, 4 marks for that, nice. Okay, so 6 marks, determine the new dimensions and fractional volume change of the rectangular prism if it is free in Z. So new dimensions are going to be figured out by the strain multiplied by the original dimensions. So here's the strategy we're going to use for this. We're going to say that the strain is equal to something times the stress. So which thing would we put here? Stress times the amount of compliance will give us the strain. And then once we've got the strain, we can figure out the new dimensions by saying that the strain in any dimension, let's say the X strain is also defined as the change in the X length over the original length in X. So that means the new length in X, if you think about how this change in length is defined, or rather minus, yeah. Final minus initial will tell you the change in that. Okay, so the new length in x, if you rearrange this thing, then you have that it is equal to Lx times the strain plus Lx, or in other words, it's the original length times 1 plus the strain. So the new length in x we'll get by taking the x strain, adding 1, and then multiplying that by the x, by the original length in x. And then we'll do the same thing for y and z to find the new dimensions of this. Then the fractional volume change would be the delta v over the original v. And the delta v would be the change in the change in volume. And this we have to be a little bit careful about. This is the final volume minus the original volume over the original volume. And the final volume would be the final length in x times the final length in y times the final length in z minus the original one. And that's not quite the same as just taking, so that's definitely not the same as just taking the change in x and the change in y and the change in z and multiplying them together. In fact, it's closer, if you want to continue this line of analytical reasoning, you can substitute in here Lx plus delta Lx, Ly, and then the same thing for y and z. So Ly plus delta Ly and Lz, delta Lz. Now if you multiply this out, then you're going to have Lx, Ly, Lz plus delta Lx times Ly, Lz plus delta Ly, Lx, Lz plus delta Lz, Lx, Ly plus some other terms, which we'll call order of delta squared, just to mean that these other terms have at least 2 deltas in them. So we're going to have like a delta Ly times a delta Lz times an Lx. There's going to be one term which is an order, which is the 3 deltas multiplied together, and that is included in this. So when you use this big O notation, it's a way to say that we've got other terms in here that are of order this thing or higher, yeah? And then we still have this minus Lx, Ly, Lz there at the end, Lx, Ly, Lz divided by in the denominator there. So the original volume and the new volume, the original volume cancels out with this part here, so the other original volume term, so that's gone, and we're left with, if we drop the big O of the delta squared terms there, then we've got delta Lx divided by, what will we be left with? The Ly and Lz will cancel, and we've got over Lx original plus delta Ly over its original length plus delta Lz over its original length, which means the fractional volume change is actually closer to just adding up the 3 strains. Okay. Now, since this question asks us to figure out the new dimensions, and we have to calculate Lx prime, Ly prime, and Lz prime anyway, which is what those are, we may as well do the actual new volume minus the original volume divided by the original volume to find out the real volume change. But once we've done that, we can check out how good this approximation was. If the volume changes are small, then this, if the length changes are small compared to the original length, so we have small strains, then this should be a pretty good approximation. Okay, let's try this out. So we figured out our stiffness and compliance matrices, and let's just suppress the output of that for the time being. Now, the next thing we're going to need to do is write out what the stresses are. So we've got a stress of 5 kilonewtons on the X, 5 kilonewtons on the Y face divided by the area of the Y face, and a stress of 3 kilonewtons on the X face divided by the area of the X face. How do we want to do this? Let's think about, maybe we'll make an L thing, which is going to be the vectors. So this is the vector length, and the L in X is 0.1, in Y is 0.4, and in Z is 0.25. Oh, these are 0.025 and 0.04. Yeah, so these are in meters now. Okay, so that's the length vector, and we'll check that this works out. Yeah, great. Now we can figure out the stress by, let's find the area first. So the area would be L. It's a vector, and it's L2 times L3, L1 times L3, and L1 times L2. Let's see if this works. Okay, so the area perpendicular to X would be based on the Y coordinate times the Z coordinate. That's how we're getting that. And then perpendicular to Y would be the X coordinate times the Y coordinate. That's how we're getting that. And perpendicular to Z would be the X coordinate times the Y coordinate. Now, what I kind of want to know is how do we, can we actually go and do things like divide the L by the A? Does this do piecewise division? No, it doesn't. We would have to go through and do that for every individual element in the thing, but that's okay too. Okay, so next what we're going to do is start writing out these forces. So we can write the force applied, also with a vector notation. In X, it is -3e3, negative because it's compressive, so we're pushing in the X direction. And in the Y direction, -5e3, and then 0 in Z. So now we've got a force vector as well assigned. And I did go and look up some neat stuff to figure out how you could do element by element division. And so I can show you how to do it in old school Maple using the sequence notation. So remember that sequence of n squared n equals 1 to 3 is just creates a list of all of the n elements there. But you can also use this to index things, force n, and that's going to create a list of the elements of the force vector that we have there. And so if you want to know the stress, then you can take the force and divide that by the area n, and this will be a list of the stresses that we've got. So the first force divided by the first area, second force divided by the second area, and third force divided by third area. Then all you need to do is say, so stress sigma is equal to the vector of these elements in a list. Let's see, where did I mess that up? Oh, this is the closing of sequence. Then we close that bracket to close that list, and then close the other bracket for the vector command. Okay, so there is the stress. Now, just an FYI, that if you have Maple 13 or newer version of this command, you can say sigma is equal to, you can just do element by element division. So this, the internet tells me that this one works too. You can take the force, and then the element division that doesn't work in Maple 11 is to put a tilde after the command, and then you need to insert a space because tilde A would be something. So put a space there and then try that out. So let me know if that works out for you. Internet says that that should work in Maple 13 or newer. But sadly, with my Maple 11 version, I'm stuck writing out the sequence. But that's okay. I mean, I kind of like sequence commands. This is sort of cool. It makes me think that I'm programming some in like a real programming language here instead of a computer algebra system. So that's kind of a fun thing. Anyway, so whatever version you use for that, you can figure out the stress vector. Then once you've got the stress vector, in order to get the strain, we're going to say that the strain comes from taking the compliance and multiplying by the stress. So there we have it. We've got our strain vector there, and the new lengths would be based on the original lengths times the strain plus 1. So that would be vector of sequence. Now we're going to take, so each length multiplied by 1 plus the strain in that dimension. And this should be the L prime vector. Okay, so we've got that. And that's the new dimensions. And we can figure out what the new, what the fractional volume change would be by figuring out the new volume. So let's do, how could we do that? New volume. Okay, the manual way to do it would be to take volume prime is equal to L prime 1 times L prime 2 times L prime 3, but typing things out manually like that is definitely for scrubs. So let's see if we can find a better way to do it. V prime is equal to product of the sequence of L prime n equals 1 to 3. Let's see if that works. This new command. Oh dang. Product. Oh, maybe this includes the sequence stuff. Product of L prime n equals 1 to 3. Does that do it? No. Okay, I've gone and reviewed what was going wrong there. So product does work just like sum, where you give it an element and then it's going to figure out what the value of that is over the list index. The problem is, for whatever reason, it can't take elements of vectors as its things that it's summing, but it can take elements of lists. So what we need to do is convert L prime to a list. List L prime is equal to sequence of L prime n is 1 to 3. And then, while this won't work, although this is an identical list of those same elements, you can use this command to add those up and get the exact same thing as we had for V prime. So maybe it looks like, in retrospect, the scrubs are taking the day here, and it's better to just kind of manually multiply those things out, since it's a lot less typing than to do it the other way. Okay, so anyway, that's V prime. And then we've got original V would be the L1 times L2 times L3. And then we've got the fractional volume change should be equal to V prime minus V over V. Okay, fractional volume change is a decrease of 0.05%. That's pretty small. So let's see how, if that compares to the sum of the strains. Now, I'm guessing this is probably not going to work either. Yeah, bad index into vectors. But if we convert that to a different container, that probably will work. And so now we've got our epsilon as a list rather than just a vector. And then if we were to sum the epsilon list, now this should tell us the sum of the strains directly. Again, we could have just manually added that up. So it's not exactly the same as the fractional volume change, but it is to 1 part in 5,000 equal. So that's pretty good and what we would have expected. Okay, so to recap, I hope it was kind of fun looking at these different. I mean, I enjoyed it looking at these different ways to sum things up in Maple there. But basically, the thing that we needed is we took our Young's modulus and our Poisson ratio. We figured out the compliance matrix. Stiffness matrix is just the inverse of that. And then we wrote out the stress by dividing the force on each side by the area of that side. Found the strain by multiplying the compliance matrix by that stress, and then took got the new dimensions by multiplying the original dimension by 1 plus the strain in each dimension. Then multiplied all those new dimensions together to get the new volume, and the fractional volume change would be the new volume minus the original volume over the original volume. And that's it. Thanks for watching.